Hey, welcome back. So at this point, we have the ability to store data in a graph structure. We wrote the graph class, we added in methods to add and remove vertices and edges, so we can store everything, we can represent a graph. Now we get to go to the really juicy, meaty, important stuff, which all has to do with traversing our graphs, searching or visiting neighbors from a given node. So we'll get into the real-world uses for this. There are many of them, just like 2 slides from now, I'll talk about it. This is also a topic that comes up a lot in computer science textbooks and final exams. It comes up in interviews, which I actually think it's a great interview question because of how many real-world applications there are. So it's not some arbitrary, just test of how much do you remember from college computer science. It's something that actually is relevant in today's world. So we'll talk about why. But when we say traversal, for now at least, I just mean visiting every single node, every vertex in a graph. So there's many ways of doing this. Usually, like when we talk about the real-world applications, you may not be visiting every single node. A lot of what people do has to do with finding nearest neighbors or most similar neighbors or finding the shortest path from one vertex to another in the case of GPS directions. So it's usually more special cases rather than visit every single node in this entire graph just to say that you've done it. But we got to start somewhere. And a lot of the more advanced algorithms are derived from our basic traversal approaches, the procedures we're going to talk about now. So when we say traversal, we mean visiting, updating, checking, searching, printing out, whatever, every vertex in a graph. So we start from one vertex, which if we go back to trees, remember trees are a special subset of a graph where for any given node, there is only one path, one and only path to get to this node. So from 17, the root, to get to 25, this is our only option. To get to 89, there's one option. Now, if we compare that with some other graphs, so the more generic graph, basically this is not a tree. Every tree is a graph, but there are many graphs that aren't. So for example, this one. This is a directed graph, which we haven't worked with very much, but it just means that those connections, those edges they have a direction associated with them. They're one way. So let's say I want to go from 0 to 6. And actually, even before that, we have a problem of not knowing where we start from. There is no root. So yeah, maybe as humans, we want to start at 0 because it's the smallest number, but there's no indication that this is the start point. We could start from here or from here. So unlike a tree, when we write the code to traverse a graph, we need to specify our starting point. So let's say I want to go from 0 to 6, for example. There is at least there's this option, 0 to 1 to 6. We can go 0 to 2 to 3 to 6, 0 to 2 to 3 to 5 to 8 to 6, and I think that's it. If this was a undirected graph, we would have some other options too. We could go from 5, we could go from 7. So my point here is that for any node in a graph, there's no guarantee there's one unique path to get there. Now, that doesn't mean that traversing is harder or more difficult, but it does mean that sometimes, there's certainly multiple orders, but also you may end up having to do some backtracking. You may revisit a node you've already been to. You almost always do. And it's not much code, but we have to write code to pay attention to that. But first, let's go back and talk about why you should care before we get into the specific algorithms. So anytime we have a graph, whether it's a network graph for a torrent website, or we're talking about web crawlers where we have, like Google in the early days, would just follow every link from one page. It still does this, but would go from one web page, follow all links on that web page, and follow them out and out and out. And in reality, it's not a tree structure because you have many web pages that link to one another. So to follow every link, that's a graph structure. So the actual process of traversing, of crawling, is just a graph traversal. Also, when we talk about things like finding the closest matches or recommendations, the shortest path between things, I'm going to show you a couple examples. These all have to do with traversing from one vertex to another. So here's this Wikipedia visualization of a small subset of Wikipedia pages. In order to create this, somebody or some code started from one web page, I don't know which one they started from, and let's say here, and they wrote code to traverse every link in this graph, and draw a little dot or something like that, and then follow one of them, followed a link to something over here, and that one linked to many other things, and from there, we went on and on and traversed all of these Wikipedia pages. So just to generate this involved some graph traversal. But that is sort of a basic example, just to draw something. If we go back to this example, when we're talking about using a graph structure to help make recommendations, this is an illustration, a poor one, of 2 video games where I'm trying to show that there's some overlap between Borderlands and Halo. Now, if we had this for 10,000 video games and we had thousands and thousands of data points for each game, and things like reviews, scores, genres, how many copies were sold, different elements of the gameplay. So if somebody said that they liked Borderlands and you wanted to figure out a game to recommend to them, or a product to recommend, or on Netflix, a movie to recommend to someone, it involves starting here and trying to find something that's most similar, that you have the most overlap with. So this is a small graph, so we can tell there's only one option, Halo. But if there were millions of other data points, we might need to traverse across them and try and tabulate what's closest, what has the most nodes or the most vertices in common with Borderlands. That involves traversing from one node to a bunch of other nodes. Or here's one more example. If we're talking about friends on something like Facebook, this very simple example, just from this, we could make a recommendation. Let's see, Maria is friends with Nan, Army is friends with Nan, and Tim is friends with Maria and Army. So if we wanted to find a recommendation to Tim, who he might know, like you've probably seen that on Facebook, you might be, I don't know exactly what it says anymore. We recommend this person, or do you know X person, or suggestions for friends. You might recommend Nan based off of the fact that from Tim, we can get to Nan pretty easily. Nan is 1 jump away. We go to Army, 2 jumps, I guess. 1 and then 2. We go to Maria, 1 and then 2. And so we could write some algorithms, traverse outwards, find friends of friends. And whichever friend of friend has the most friend of friend, that's a bad way of putting it. Whoever looks closest, whoever has the most friends of friends with me, recommend them. Okay, so my point is there's lots and lots of applications, even things like artificial intelligence. If we talk about all the different possibilities for a board game, a layout in a game, like tic-tac-toe is a simple example, but let's say something crazy like Scrabble, where there's so many options. You could use a graph to store different game moves and then traverse that graph to find the shortest path to a winning move, the shortest way to win the game, for example. GPS navigation. We have millions or billions of vertices representing a map and intersections and businesses. How do we find the best way to get from one place to another? So that doesn't involve just direct traversal. That involves finding the shortest path, not just blindly traversing the entire graph. But we have to start somewhere before we can talk about shortest path algorithms, before we can talk about making recommendations. We just need to be able to visit every single node. And there are many ways of doing that, just like with trees. So in this section, we're going to talk about depth-first search or depth-first traversal, both recursively and iteratively. And we're going to talk about breadth-first traversal. Now, it's not that different from what we did with trees, but remember the distinction that I showed. There are times where you're going to have to visit a node again or realize you've already visited that vertex and adjust accordingly. But I'm getting ahead of myself. Let's now talk about depth-first search and how it works in the next video.